So, first of all, I have to thank the organizers for having, for convincing people to be speakers at this conference, including me. I will talk about topological recursion, which is the thing I've been working on for many, many years. I will give a very introductory talk. It's maybe something you have already seen, already heard about. I will be, so it's about topological recursion is a mathematical structure, and it started about the problem of counting surfaces. So I will try to show you how it has appeared. You've probably seen this picture sometimes. It has more or less become my logo. So what I'm going to present is a subject which I find very fascinating, very exciting. So let me start by this simple problem of counting. So we are going to count surfaces, and we are going to start by counting discrete surfaces. So surfaces made by gluing polygons. It can be any types of polygons. That's what mathematicians call maps. A map is indeed a gluing of polygons on the surface. For instance, on the Earth, the polygons are countries on seas. We will have maps on spheres, maps on surfaces of different genus. So, let us start by this simple problem. Counting quadrangulations. So, maps made of quadrangles that have 4 sides. So this is a quadrangulation of a sphere with 6 quadrangles. You can see 1, 2, 3, 4. 1, 2, 3, 4 quadrangles here. But this face is also a quadrangle, and this face is also a quadrangle. There are 6 quadrangles. In order to avoid double countings, we shall mark one edge with an oriented edge on the surface to avoid symmetry factors. So in how many ways can you cover the sphere with 6 quadrangles? In how many in equivalent ways? Well, I tell you the answer. This is about 24,000 ways. But in the 60s, Tutt found a general formula for counting the quadrangulations of a sphere with k quadrangles. It's given by that. The first few numbers are 2, 9, 54, and so on. Let me show you what the 2 corresponds to. So 2 quadrangles. So these are the 2 quadrangulations. So you have one quadrangle with one marked edge, and there are 2 ways of holding it such that it gives a sphere. I have a quadrangle here. Okay. So one way is this one. One way is this one. Now let me show you the possibilities with 9. You now have 2 quadrangles. So one obvious way is you glue them to each other like that. It's a sphere. It's topologically a sphere. And another way is, for instance, this and this, and you glue them together. This is a sphere. And there are 8 possibilities to place the arrow edge, so that makes 9. Now, out of these numbers, you can make a generating series, 2t plus 94 and so on. So this is a series which happens to be the Taylor expansion of that function, which you cannot see on that board. You can see it in the other on the sides. So this is a function of t. And let me replace this square root of 1 minus 12t by this variable r. So in the variable r, this series is rational. Okay. Now let's ask another question. Now let's count the quadrangulations of a sphere with, let's say, 4 quadrangles on an another face, a face which is not a quadrangle, which has length 6, it's a hexagon, and the marked edge being an edge of that face. in fact, oriented such that the special face is on the right of the marked edge. So in how many ways, for instance, can you cover the sphere with 4 quadrangles on 1 hexagon, and the number is 225 possibilities. And again, Todd found the general formula, which is that one. So for K quadrangle on a marked face of length 2L, this is the number of possibilities. Again, you make a generating series with T to the number of quadrangles on Z to the power of 2L plus 1, where 2L is the size of the marked face. Again, this series is the Taylor expansion of the function of T on Z, which is algebraic, as you can see. And again, R is square root of 1 minus 12T. You can plot this function as a function of Z at fixed T, and this is what you get. Let's call this Y. You plot Y as a function of Z at fixed T. It looks like that. It's a multi-valued function. And of course, as I said, it's algebraic. There is an algebraic relationship between Z, Y, and R, where it's a polynomial. So there is a polynomial. We shall call it a spectral curve. In fact, well, so first remark, everything is rational in this variable R and not in T. T was our original variable associated to our counting problem, and R is a variable more convenient to describe the spectral curve. On the map between T and R, we shall call it the mirror map, in analogy with what happens in string theory, for instance. And also, let me call this function W01. 0 is because we are talking about the sphere, genus 0, and 1 is because we have one special marked face. And we shall see other counting functions like that with other genus and other number of marked faces. Another remark is that this function y as a function of z, in fact, it should be viewed as z should be looked at as a complex variable, and y is a complex variable. In fact, if you think of it, you should not plot the function in R cross R. So here I plotted real part of Z, a real part of Y versus real part of Z in R cross R. But in fact, you should plot this function in C cross C. And in C cross C, the curve is a complex curve. So one-dimensional complex curve is in fact a two-dimensional real curve, so a surface. So in fact, a complex curve is really a surface embedded in C cross C, in the four-dimensional space C cross C. So a complex curve is in fact a surface. And this is the same surface as here. Here, in this axis, it's real part of Z. That axis is imaginary part of Z, and the vertical axis is imaginary part of Y, whereas here I was plotting real part of Y. This surface, we shall call it the spectral curve. It will play a very important role. So now let's go to the next case, which is now we want to count the number of quadrangulations of a sphere with now two special marked faces each. Each having a special an arrow on one of its sides, and you can check by. It's easy to see that the length of the two faces must have the same parity, and it's better to parameterize them this way. L1 is A plus B over 2, L2 is A minus B over 2, and let's count. So, and here is the formula for counting the number of quadrangulations with K quadrangles on two special faces of respective lengths, L1 and L2, given by this formula. So this is the formula. I don't think this one was given by Todd, but it could have. And again, we make a generating series. T to the K, Z1 to L1 plus 1, Z2 to L2 plus 1. And we call that function W02. Again, 0 because we are talking about the sphere, which is genus 0, and 2 because now we have two marked faces. And on this, you can resum that series, and it is the Taylor expansion of that function. Well, you can say, well, nice, it's a beautiful rational function, well, algebraic function, there are square roots, but in fact this function is even more beautiful than that. It's a very, very special function regarding our spectral curve. It's a deep geometric object on the spectral curve. Let me describe it this way. It's related to a green function, in fact to the second derivative of a green function on the spectral curve. It's also called the fundamental second kind form on the spectral curve. Sometimes it's called the Bergman kernel. It's a very special geometric property of the spectral curve. Let me try to describe it this way. So remember our spectral curve was this function W01, the one I plotted before, and which is in fact a surface embedded into C cross C. And this surface, in fact, can be conformally mapped to the Riemann sphere. It's conformally equivalent to the Riemann sphere. There is a conformal mapping to the Riemann sphere. Let me describe to you how we can compute W02 geometrically. So we take Z1 and Z2. They are points on that surface. We see where they are mapped on the Riemann sphere, so they are mapped at 2 points on the Riemann sphere. Now place an electric dipole on one of the 2 points. It creates an electrostatic field on the sphere, and measure the value of the electrostatic field created by dipole at point 1, measure it at point 2. It gives the value, and this value is W02. So it's a very geometric property. Now let's go to higher genus and higher number of special mark faces, so either higher genus and possibly higher number of mark faces with respective lengths L1, L2, Ln, okay, and K unmarked faces. And again, we make a generating series which we call WGN. G stands for the genus, the number of holes, and N for the number of marked faces, of special faces, which we can look at like boundaries. And what is the formula for WGN? I showed you already some formula for W01 and W02. What is the formula for WGN? So let's start by genus 0 and 3 marked faces. Here is the formula. This formula is not as explicit as before, it's given as a residue. This residue is extremely easy to evaluate, but I didn't evaluate it because I want to show you the general structure. So it's a residue taken at two special points, square root of 8 over 1 plus r, and there is a prefactor, which is an algebraic function of this z, and times a bracket where you have W02 of ZZ2 and W02 of ZZ3, which we have already computed. Now let's look at another case. This is genus 1, so one hole, and one marked face, which I put on the exterior here. The marked face is the exterior face. Again, there is a residue formula, which takes that form. It's a residue at the same points, and with the same prefactor, but just what is inside the bracket is different. There is a W02 of ZZ. And the general situation, G and N marked faces, will take more or less the same form. Again, there is a residue formula with the same prefactor, and what changes is only what is inside the bracket. And this formula allows to compute recursively all WGNs, and the recursion is on the recursion is on the Euler characteristics. So all the terms, all the WGNs that appear in the right-hand side have lower Euler characteristics than the one you want to compute. So if you want to compute a WGN, you can do it by this formula in a number of steps equals to the absolute value of its Euler characteristics. And you can compute all of them in this way. So let me summarize it. there exists a certain operator kernel, so basically this is multiplying by this prefactor, and the star means taking the residue. The residue is an integral. It's you can formulate this a little bit like Feynman graphs. So let me summarize it again this way. It allows to compute all the WGNs by recursion on this number 2g plus n minus 2, which is minus the Euler characteristics. And that's why this is called the topological recursion. It's a recursion on the topology. And it allows to compute every WGN, knowing only at the beginning W02 and W01. And also I told you that W02 can also be deduced from W01. So if you know only W01, you can compute every WGN. In fact, this formula works for quadrangulations, but it works for all sorts of maps, triangulations, on maps made of pentagons, hexagons, or whatever. It's the same formula that works for all of them. The only thing which is different is W01. And you can illustrate this formula by this picture. If you want to compute WGN with a certain genus and number of holes, you have, well, I illustrate this kernel by the piece which is here, which is on all the brackets here are either products of W's, or a W of G minus 1. And somehow this kernel is the piece you add to make this new surface. And if you look at it, it looks like a pair of points that you remove, except that in fact it depends on only two variables, so it's like it has two boundaries. So in fact you should more think of it as a cylinder where one of the boundaries is pinched. Well, you can call it the pair of points without the legs, or the short, if you want. So now let's go to another problem, which is to count hyperbolic surfaces. Well, hyperbolic surfaces are surfaces with a metric of constant curvature minus 1, and let's define MGN of L1, Ln, the set of all hyperbolic surfaces with n boundaries that are geodesic with given lengths. So this is a set of surfaces. And we shall put a measure on it. To write the measure, I will use a system of coordinates. And to find coordinates on this space, observe that you can decompose any hyperbolic surface into pairs of points. So we shall decompose into the elementary blocks, which are pairs of points. So you can cut the surface with geodesics, with closed geodesics. And now record the length of each closed geodesic. And also, vice versa, when you have pairs of points, if you glue them together, you can reconstruct any hyperbolic surface. So to glue together two pairs of points, they must have the same boundary length, so that you can glue the two circles together. They must have the same length, but you can rotate by an angle, by a twisting angle, arbitrary. And so, if you record all the lengths on the twisting angles, this is a set of local coordinates in that space. It's only local coordinates because the way you decompose into pairs of points is not unique. But nevertheless, this allows to define a volume form. The volume form is just the product of dl d theta. It's a volume form in that space, and this allows to define the volume of that space. This form is in fact independent of how you cut into pairs of points. So, the first few volumes have been computed a long time ago. Well, V03, this space is the space of pairs of, the surfaces in the space M03 of L1, L2, L3 is a pair of points with three given lengths, and there is a unique one. So the space M03 is made of 1 point, and its volume is 1. But for M11, it's more complicated, but the formula was found long ago by difficult computations in hyperbolic geometry. For V04 also it was found. And observe that it's always a polynomial in the square of the length. It's not obvious at all from the definition. And the question was how to compute volumes for higher topologies. It's a difficult problem. And it's difficult, especially because the decomposition into pairs of points is not unique. Well, you can see it here for the same surface. You can see obviously two ways of cutting into two pairs of points. For that surface too, you see I could have chosen bad geodesic, or I could have chosen bad geodesic. There is an infinite number of ways of cutting into pairs of points, and that makes the computation extremely difficult. The problem was solved in 2004 by Maria Mirzaani, and she got the Fields Medal for having solved this problem, and she gave a recursion formula for those volumes. Before writing the Mirzaani's formula, in fact, I will, instead of writing Mirzaani's formula, I will not write the recursion for the volumes, but for their Laplace transforms. So we just Laplace transform the volumes by multiplying by e to the minus I and integrate from 0 to infinity. And now that's a function which I call WGN, it's not an accident, of Z1, Zn, which are the Laplace transform variables. And so in 2004, Maria Mirzaani found a recursion formula which, written in Laplace transform, which we did with my student Oranta in 2006, takes that form. So again, it's a residue with some kernel of a bracket, and the bracket is exactly the same we had for counting discrete surfaces. Exactly the same thing in the brackets. So recursion on the Euler characteristics. But the kernel is different. The kernel involves a sine function. And W02 also is that function. Again, it is the fundamental second kind form on a certain Riemann surface. So again, this allows to compute all those volumes by recursion on the Euler characteristics, and it takes the same form. So here I will flash this slide just to show. Okay, let me go to the end of that slide. Just to show that this formula makes extremely easy to compute any volume, because taking residue is something very easy, and if, for instance, you want to compute W11, you have to compute residue as z going to 0, so it just means you have to expand everything around z equals 0, and somehow the most difficult part of the computation of the volume using this Mirzaani Laplace transform formula, the most difficult part of the computation is to write the Taylor expansion of the sine function. So it's extremely easy in this way. So now we have seen two examples where we find very similar formula. So we started, so let me summarize what we had. We had already, so imagine we have already computed the disk amplitude. So the number of surfaces with genus 0 on one boundary. So things like that. And it gives what we call the spectral curve, which is a certain Riemann surface embedded into C cross C. Okay, let's say it's given by Tot for maps, or it's given by God, or I don't know. Let's say it's given, W01. Now, to find W02, so the number of cylinders, that is genus 0 surfaces with two boundaries, you just take the fundamental form on that surface, and it gives you W02. Now, if you want to compute WGN, there is a recursion formula. There is a certain kernel, and the kernel, in all cases, took that form. So it's an integral of W02 divided by W01. I won't explain all the details, but it's basically, if you know W01, then you know W02, then you know the kernel. And then the recursive formula is always the same for all those problems. Discrete surfaces, hyperbolic surfaces, and in fact many other problems take exactly the same form. Now we have the idea, but in all this residue computation, all what you need to know is that you have analytic functions. You don't need to know that this came from a problem of counting surfaces, of counting discrete surfaces, of counting hyperbolic surfaces. In fact, you don't need to know anything except the fact that W01 is an analytic function to do this computation. So, what happens if you start from your favorite function f of z, instead of starting from a function which was given by an enumerative geometry problem? What can you do if you start from a really arbitrary function? So that's how we define invariance of the curve. So you pick an arbitrary spectral curve. It can be given by the solution of a certain polynomial equation, or in fact you can replace P by not a polynomial but any analytic function of two variables, or you can start from a Riemann surface embedded into C cross C, or embedded into, in fact, more general spaces, but also works. Well, in string theory language, that would be what you call the target space. You can choose almost anything. And then you define its invariants. You define them by the formula I just gave. So W01 was Y. In fact, let me make it a differential form. Let me multiply it by dx and say that now W01 is not only Y, but Y times dx, a differential form. W02 is the fundamental second kind differential on the curve, and WGN is given by this recursion formula. Exactly the same. And we call that the invariance of the spectral curve. So, let me summarize. Topological recursion is now a definition that to a spectral curve associates a sequence of forms, WGN, that you call its invariance. So let's call that the invariance of a spectral curve. It's just a definition. Why would that definition be interesting or useful? Well, we already saw that this definition is useful because it has applications. It solves some enumerative geometry problems. It counts the number of maps, it counts the number of hyperbolic surfaces, it counts plenty of other things, so there are plenty of other enumerative geometry problems which can be formulated in that way. But beyond that, it's one of them, the invariants defined this way have amazingly beautiful mathematical properties. Whatever you like in mathematics, basically is there. It's some of the most fascinating mathematical objects I have seen ever. For instance, they are modular invariants. Modular invariance is a very strong property in mathematics, and it's there. They satisfy, for instance, Seiberg-Witten equations. Out of them, you can build tau functions, integrability, solutions of Hirota equations. You can find solutions to Virasoro equations. And they have nice behavior under limits, which is usually something very hard to obtain. So they are really beautiful mathematical objects. And in the recent developments, we are really studying how they are related to tau functions. And, I won't have time to say much more about that. Let me, I see that time is almost over. I wanted to give the example of Gromov-Witten invariance, so another counting problem. Let me do it very short. So, let's start from this counting problem. In the plane, how many lines go through 2 points? Well, you all know the answer. There is one line through 2 points. How many conics, so degree 2 curves, go through 5 points? Well, maybe you know the answer. Again, there is a unique conic through 5 points. Now, a degree 3 rational curves. How many degree 3 rational curves go through 8 points? Well, the answer is 12. This is not so obvious. So now you can ask how many degree D rational curves go through 3D minus 1 points. And these are the first few numbers. Let's call them N0 of CP2D. In fact, by rational curve here, I mean, in fact, a line is an equation of degree 1 not R cross R, but I will again look at it in C cross C, or in fact CP2. It's an equation in CP2, it's a complex equation in CP2 of degree 1. Here it was a complex equation of degree 2. And in fact, again, a line should be thought of as a surface in C cross C. And rational means that this surface has genus 0. You can ask the same question with surfaces of genus 1. These are called elliptic curves. And again, you can ask the question, how many degree D elliptic curves go through 3D points in CP2? And these are the first few numbers. There is no elliptic curve of degree 1 or 2. Elliptic curves must have degree at least 3. And the general question is, how can you compute those numbers? These are called the Gromov-Witten numbers. And these are examples of the simplest string theories which are topological string series. So in how many ways can you embed a Riemann surface of a certain genus and a certain number of mark points into a target space? Here CP2. So I just give you the answer. This is again given by topological recursion. So I will skip the next thing because I'm a little bit late, or maybe we started late. But let me conclude. Topological recursion is a universal equation satisfied by many geometric invariants, by many enumerative geometry problems. And what I showed you is that, another remark is that it's very easy to implement. It's completely automatic. It's just computing residues. So any Mathematica or any software can do it. And it can be used to define new invariants, the invariants of spectral curves. And these are very useful. And as I showed you, many known invariants, like Gromov-Witten invariants, are special cases of the topological recursion invariants. And they have really amazingly beautiful mathematical properties. And they have already found many applications, but there are many more to come. I did not have time to describe all of them, but for instance, there is knot theory, random matrices, 3D partitions, so what people also call like melting crystals or things like that, are also have their asymptotic expansions controlled by topological recursion. So thank you for your attention.
Thank you very much. We can finish. You have time for questions for Bertrand.
Which one?
Well, I don't know the beginning, for instance, the topological, topological recursion. I mean, it's obviously true, but is it a theorem?
Well, for discrete surfaces, for quadrangulations and all that, yes, it's proven. It was proven in 2004, and the proof basically it's the same proof as what Tutt did for just counting the Gini 0 one phase case. It's exactly the same proof that works for all cases, and it's perfectly correct mathematical proof. It's not fully satisfactory for combinatories because it's not a combinatorial proof. It uses some non-combinatorial steps, but it's a proof. For string theories, it's proven for all toric Calabi-Yau cases, which is not all string theories, but it's proven for a large variety of string theories. But for instance, for knots, this is a conjecture. For the knots, this is not proven. And in fact, if you could just prove the 0-1 case for knots, it would already be, it's already a 20 years old conjecture, which is considered as one of the greatest challenges in topology at the present time. So proving the conjecture for all G on N would be really hard. For random matrices, it's not proven in all cases. Well, it depends.
Other questions?
About the Mirza-Rani formula. So, did she use this method, or is it just a remark that you made after that a formula is
no,
efficient to work?
She didn't use that method. She proved the formula, and we saw that the formula was a special case of the general formalism. And then we found another proof of Mirza-Rani later using topological recursion. But no, she did not use it. We did the other way around. We used Mirza-Rani's formula to find that it was an example of topological recursion.
What is the relation between the surface you introduce and these surfaces?
Well, so the surfaces you want to count on the spectral curve. Well, it's somehow the same relationship in string theory between worldsheets and target space. So the surfaces you want to count are worldsheets, and the spectral curve plays the role of a mirror of the target space. On mirror symmetry is something really complicated. It's not obvious when you start from a given target space to guess what the mirror is, so to guess what the spectral curve is. In fact, a large part of the game here, to answer also Hubert's question, is to find the good spectral curve corresponding to a given numerical intellectual problem.
Other questions for Bertrand? No? Okay. If not, let's thank him again.